So welcome to this lecture on combinational logic. Now you should probably already know that we have figured out how to use semiconductors to make transistors that can implement an and, or, and not operations. And each one of these is considered a gate or a digital gate, and we can use these gates and combinations to create a digital circuit that will produce some sort of useful output. So we'll have some inputs into the circuit. Under certain conditions, the output can go to a high voltage, turning on a light or something, or a low voltage, shutting off a light. So then our computer can, or our circuit can make decisions. And out of this circuit, we can build eventually an entire CPU that can run all of the programs that you guys have seen running, including games and all that fun stuff. So it all starts on this just nice basic level. So what we want to do in this lecture is figure out how we can use these and, or not gates to make a useful circuit for us. Now, as an example, I am going to create a circuit that will tell me when to go surfing. I like to go surfing, and let's assume that I have some sensors that can sense whether they're waves and wind or sharks in the ocean. And when it senses those things, it'll turn on a wire or put on a voltage onto a wire so that my combinational logic circuit can tell me when I should go surfing or not. So, of course, when I want to go surfing, there needs to be waves. So the W represents whether or not they're waves. And I have some sort of sensor that measures the waves, and when the waves get to a certain height, it turns on this on a wire to a high voltage, and I can detect that there are waves. So also, if there's wind, and I can't use W for wind, so I'm just going to use I for wind, and that again, I have another sensor that will sense whether or not there is wind. And finally, a sensor to sense whether or not there are sharks in the water. So I have these three sensors, and what I want to do is create a circuit that tells me when I should go surfing. And so my output will go over here. Now, this is called a truth table. You've probably seen these truth tables if you studied propositional logic in maybe a discrete math class or as something else. And basically, I want to every possible combination of waves, winds, and sharks, and I want to, under all of those different combinations, I want to know whether or not I should go surfing. So let's go ahead and fill out all the combinations. And with this, I'm just going to start counting in binary. And that will give me all the different combinations. Now using 3 bits, that gives me a total of 8 different outputs. So here are all the different possible combinations where there are no sharks, no waves, and no wind, to there are sharks, wind, and waves. And so when would I want to go surfing? Well, I can fill out this in the output, so I'm just deciding this off of the top of my head. Now, for me, I don't really like to surf when there are no waves. I just sit there in a flat ocean. So, of course, I'm not going to want to surf under those conditions. Now, if there are waves and no sharks and no wind, that is probably really good surfing conditions. So I'll want my output to be on to tell me to go surfing. Now, if they're just wind and no sharks and no waves, again, there are no waves, so I probably don't want to go surfing under that condition. Now, under this condition, there is some wind and there is some waves, but that might be okay. Maybe the wind won't be too bad. At least there are no sharks here. So since there are no sharks, I'll go ahead and, hey, give it a try. Tell me to go surfing. Now, under this condition, there are only sharks in the ocean. Yeah, no thanks. I don't want to go surfing. Now, under this condition, there are waves. There's sharks, but no wind. Now, since there's no wind and waves, maybe I'll chance it. The sharks probably won't want to eat me anyway, right? So maybe I'll go surfing under that condition. Now, if there's sharks and wind, but no waves, of course, I don't want to sit out in the ocean and just be shark bait, so I won't want to go surfing then. And finally, under this condition right here, this last condition, where there is a shark, wind, and waves, the wind might kind of mess up the waves, and why would deal with a shark under those conditions? So yeah, no thanks. I don't want to um, chance getting eaten by a shark if the waves aren't going to be that good because of the wind. Now, on some of these problems, you'll just be given this truth table, and other ones you might need to figure out the output of the truth table, and we'll review that a little bit later in this lecture. But now what I need to do is I need to create a circuit that will produce this output once I connect it to my three sensors that sense whether there's sharks, wind, and waves. And the way that we can do that is there's two ways that I'll teach you, and the first will be sum of products. And you'll see why it's called that a little bit later on. And we might abbreviate this as SOP, or sum of products. So in sum of products, we ignore all the lines that are zeros. So we don't have to worry about any of those lines, and we just focus in on the ones. So whenever we have a 1 on a line right here, what we do is we write down a term and we look at the W. Okay, so the W on this line is high. So I'll just write down a high W, or the W. And then if you notice on this line as well, the wind and the sharks are both a low voltage. So I will write them down, sharks and wind, and we'll negate them. So to show that you negate them, you can use the apostrophe. And another thing, it could be just a line over the top. That just means this value inverted. So negate is going to be this not operation, and that means to take the zeros and turn them into ones, and take the ones and turn them into zeros. But we're not going to negate the wind. So basically, when I hook this up to my shark sensor, I'll put a not gate in there to get the inverse of whether or not there's a shark. All right, now let's pick out the other ones. So we have two more that we need to do, and we'll just write out the terms. So this will be negate the shark, and then the I and the W are high voltages here, so we won't negate them. And then on this line, the only one we'll negate is the wind. So you can see the S is a high voltage, the I is a low voltage, so we negated it, and the W is a high voltage. And same for this line, the S is a low voltage, so it's negated. So now that we have all the ones and we wrote down these terms, all we need to do, and by the way, this is like multiplying, and you know in math when you write A5 or 5A, that you multiply the 5 and the A together. That's the same with this, but our multiply operation is the AND operation. So this is these three inputs ANDed together. And finally, that's the products, by the way. So here are our products. And the sum operation is this OR operation that we actually use a plus sign for. So our final Boolean algebra expression will be these three terms summed together. And now that's it. We have a Boolean expression that we created out of this table. Pretty easy, right? Just to review, you pick out the ones. As you pick them out, you write down the term or the product for each line, where you take the zeros and you negate those, and the ones and you don't negate them. After you have all the terms written out, just sum them together. Okay, and so this is the final answer of Boolean expression. And next, I'll show you how you can take this Boolean expression and build it using a digital logic simulator. But before I move on, I'll show you the other way that we can come up with one of these expressions. Now, the other way is called product of sums. So we've switched those. and you might abbreviate that as POS. So whenever you see that, just remember, okay, S is sum, P is product, O is the of, and sum of products, and then hopefully you could say, okay, my products are summed together, and this is going to be the exact opposite of this. Everything we're going to do is going to be opposite of what we did in sum of products. Now, normally you would not do both of these at the same time. You choose one method and get your equation, build your circuit. But I'm just trying to teach you how you can do both of these methods. And so now I was able to come up with this equation using this method. I'll come up with another equation that uses this method. And again, everything is the exact opposite. So before we picked out the ones, right? So now we're going to pick out the zeros. So we're doing product of sums. We're going to pick out the zeros. And so we'll go ahead and write down our three terms. We got our S, I, and W. But instead of multiplying them together, we're going to sum them together. Okay, now here, when it was a low voltage, we negated it. Now when it's a low voltage, we do not negate it. So none of those are negated. So again, everything will be opposite. Now let's try this line right here. Okay, so we'll write our S, I, and W, and we're going to sum them together. And now we see that this is low, so we do not negate that. This is low, so we do not negate the W, but I is high, which means that we need to negate it. So there's that apostrophe. And again, if you don't want to use apostrophes, you can use a line above the letter as well. All right, next, let's pick out the other ones and put them down. Or actually the other zeros, let's pick out the other zeros and put them down. All right, so if we look at this line, all three are high voltages, so all three are negated. This line, the first two are high voltages, so they're negated, and this one is not. Then on this line, the only high voltage is the sharks, and it is negated. So these terms are now our sums, and we just multiply them together. And so writing down the final equation for our product of sums, and I ran out of room to complete it all on this line, so it just continues over here. And it's just all of these products multiplied together. Now, remember, products are the AND operation, and the sums are the OR operation. So now we have two Boolean expressions. Now again, you would only do one. You'd only choose either this one or that one. So what one do you want to choose? And at this point in the class, it really doesn't matter. But if you want to save yourself work, you might want to count the number of ones. If you notice, there are only 3 ones here. And so since there are only 3 ones, this is going to be a smaller equation. And there happen to be 5 zeros. So this is going to be a larger equation. So you might want to save yourself some work and choose the one that's going to be smaller. So this one has 3 ones, so there's only going to be 3 products versus 5 sums. Now, up here we have our AND gate, our OR gate, and our NOT gate. Now, usually AND gates are really made out of only 2 inputs, but just for convenience, the Logisim lets you put down one AND gate, and you can change the number of inputs that it takes it in. But really, all of that is doing is taking 2 AND gates, putting it like this, and we'll make that just a 2-input AND gate. So if we wanted 3 inputs, it takes the 2 AND gates, combines them together, and then that makes it 3 AND gates like that. So even though Logisim makes it look nice and pretty, which is really nice for us in the real life, if you're going to make this out of real digital circuits, you would need to you would need to put AND gates like this, or by other chips that have AND gates that have different amounts of input. In fact, circuits do not look like this. AND gates do not look like this. They're actually very microscopic. You can't even see them with your plain eye. This is just a way to draw them so that you can see your circuit. This isn't how they look in real life. And this symbol is an AND gate. And in fact, if you're an electrical engineer, you might have a ruler that has a stencil for AND gates and OR gates, and you put it down and you draw your little AND gate. So this is just a way to visualize our circuit. It isn't how the circuits are really built. But we'll use this, and this is a great program to learn how to build digital circuits. Unfortunately, we don't have the actual hardware, and it would take us forever to actually wire everything up. So we're going to use this, simulate it using this Logisim. Now, this is the equation that we came up with our product of or our sum of products. So this is our sum of products, and now let's go ahead and make our input. Right here, this is called an input pin, but it can also work as a switch. So and you'll see why it's called an input pin later on, but you can see that I can kind of turn it on and off. So this one, I'm going to pretend like that's my shark sensor, okay? So I could go down here and label it, and let's go ahead and get another one for our wind and another one for our waves. So we can pretend like these hook up to some sort of sensor that is somehow able to sense whether these there are sharks or not, or there are waves or not. So just pretend like we actually have those sensors. And now we want to build our circuit. So we want to AND these three things together. So we can grab our AND gate. And in fact, we're going to need 3 AND gates. And though each AND gate is going to have 3 inputs. So I'm going to go ahead and place down my 3 AND gates like that. Okay. Now we see in this first AND gate that the shark and the wind are inverted. That's this one and this one. So we could go ahead and place NOT gates in between them and hook up our shark. And you're just like dragging these wires to the right input. So, and then our waves are not inverted, so we can hook that up here. Okay, now if you notice, the NOT gate has this little symbol, a triangle with a circle on the end of it. So that circle could kind of be like a NOT gate. And in fact, we can actually speed this up. Logisim is really nice. Now the NOT gate is really still there. You have to put that NOT gate in, but Logisim lets you combine the NOT gate with the AND gate. If you see here, we can negate certain inputs and kind of put a NOT gate right on that input. So we know that the shark and the wind want to be there. And you see that little circle represents a NOT gate. So these are just shortcuts in the way that you draw this. Remember, this isn't how circuits really appear. It's just a little shortcut to be able to draw it together. You can imagine if you're an electrical engineer and you had to do big circuits like this, you'd find every way where you could save a little bit of room and a little bit of drawing. So you can just put little circuits there as a NOT gate. So here's our next AND gate and our final AND gate. So the shark on this one is inverted, so that's the first input. So I'm going to negate that. And none of the last ones are negated, so I'm not going to negate that. So we'll go ahead and hook up our shark. Now be careful, don't draw these wires over each other. You see how they connect? That little dot says they're connected. So we don't want to do that. Control Z will undo that, but now we can drag it across, and as long as I don't drop it on another wire, it doesn't connect it. And see, there's no dot there, so they're not connected. And then we can take our wind and connect it there. In fact, sometimes it's just easier to connect them all up together. And finally, the waves, we'll hook those up there. And now we need to sum them together. So then we're going to grab an OR gate, which is our sum. And so the OR gate has this more of a rocket ship kind of look. and it needs 3 inputs. So go down here, change the number of inputs to 3, which gives us 3 wires, 1 output. Nothing's negated, so we can just hook that right up. Now, we can grab this little output pin right here. So, and it's kind of like a light bulb, and whether it's on or not. So remember, there aren't any waves. Remember, I said it's really good. I want to go surfing when there's waves. I turn that on. You see that voltage turns high. We can see that that actually activated this AND gate, turned on that circuit, and went high there. So remember, an AND gate, if all the inputs are high voltages, then its output will be a high voltage as well. So it goes through the NOT gate, we can't see it, then it becomes a high voltage, this too, and so we have 3 high voltages, and that turns on the AND gate. Okay, so remember I said I'd go surfing if there were wind and waves, and sure enough, that turns on. So what I'm doing is I'm verifying that this circuit works correctly. So I probably would want to pull up my truth table, turn in my different inputs, and make sure I'm getting the right output. And then I said that I would go surfing if there were good waves, no wind, and a shark, and it's not on there. And so I'm going back, and you might have noticed at first I forgot to put that apostrophe on this I. That's when I copied it over to this program. So that meant that this AND gate isn't hooked up right. So I'm not getting the right output. I need to go back and figure out what I did wrong. This thing should be negated, and that's this wire right here. So grab our edit tool. By the way, this is our edit tool, so we can grab things and edit it. This is our poke tool that allows us to change our switches. So grab our edit tool, I select that one, negate that middle wire, and sometimes it draws a little extra circle there, but you can kind of pull your gate. And that's actually a good way to make sure you got your wires connected, make sure it kind of connects to it. And then now, of course, we're going to go surfing then, but I won't go surfing if there are no waves, even if there's shark or wind or any combination of that. And I can verify that I got all the right output. So now I did my sum of products, or sum of products equation. So now let's go down here and do our product of sum. So what I did is I just grabbed my OR gates. Remember the sum is an OR gate, and there's 3 inputs into each one. So I grabbed my one OR gate, I changed the number of inputs to 3 before I placed it down, and then I placed 5 of these down. Then I grabbed an AND gate, changed the number of inputs to 5, and placed 1 AND gate down. After I placed those down, then I just connected the wires up here, and then I looked at my equation. Okay, none are negated, so I have an OR gate. I selected the OR gate, didn't negate any of them. The middle one's negated on this one, so I put the middle negated there. The shark is negated, that's the top one. Then the first 2 are negated, and then all 3 are negated. So after I did all of that, then what I did to make this fast, I just grabbed my shark input, I dragged it all the way down and connected it up to here. And then I could just connect it across. And then my wind, I did the same thing, and then connected all the middle ones there. And finally, my waves, I connected to the bottom, and then connected all of the bottom ones to that. So that kind of made that fast. And if you look, of course, now I have 2 circuits that do exactly the same thing. This one was made using sum of products, and this one was made using product of sums. And you can see it has AND gates with an OR gate, and in this case, it has OR gates with an AND gate. But if you look at these, we're always getting the same output for each input. So these 2 circuits are exactly the same. So of course, I wouldn't want to build both of them. I just build the one that's smaller. And so this is the smaller equation, so it was faster to build than this one. Now, you usually want to choose the smallest equation because these gates cost money, and you want to save yourself money by using fewer gates than more gates. So the smaller your equation, the smaller your circuit, and the less money it's going to cost to make it. So that's how we can create a circuit using sum of products and product of sums. Again, you wouldn't do both of them. You just choose the one that's the smallest. But I wanted to show you how you can make both of them. So that's why I did both of them in this video. But if you're doing it on your own for your homework, you would only choose the smallest one and make that one. Now let's talk about what you're going to do in the lab. We are going to build a circuit that's going to add numbers together. Now recall when we added binary numbers together that we added them bit by bit. So we added these two numbers together to produce some sort of output and then some carry that we took into account when we added the next two bits together. So we're going to do that. Now, just so we add these numbers together, we add a 0 and a 1 together, and that produces a 1 output and a 0 as the carry. Now we can add these numbers together, and 1 plus 1 plus the carry in becomes 2. So that's a 0 with a carry of a 1. And next we can add these three together. And again, that's 2, so that's 0, carry a 1. And these can keep going. And our final answer becomes that. Now, instead of building a circuit that takes in these 8 characters, now in our computer, they're actually going to be 16-bit numbers, so really twice as many numbers as you see here. Instead of taking in all of the numbers at once and adding them all together, we'll make a circuit that focuses on a smaller problem of just adding these 2 bits together. So we'll get one input from one of the numbers and another input from the other number that we want to add. We'll also grab another input for the carry in. And this is the carry in from the previous bit. So this one is the carry in from that bit. Now our circuit is also going to produce 2 outputs. And I only showed you a circuit that produced 1 output before, but don't worry, 2 outputs is easy. It's just really 2 problems in one. So our circuit's going to produce 2 outputs. It's going to take these 3 things in as input, then it's going to produce the answer as an output and also the carry out. We're going to take the carry out and feed it into the circuit that adds the next bits up together. So once we have a circuit that does this operation, so it takes in a carry in and 2 numbers, produces a result and a carry out, we can place 16 of them down and it will add a 16-bit number together. Now the very first one that we place down, we'll just hard code the carry in to be 0 all the time, and then we'll take the carry out of this circuit, feed it into the carry in of the next circuit, the carry out of this circuit, feed it into the carry in of the next circuit. Now this circuit is called a full adder. So let's make a truth table for the full adder. Now remember, the inputs are the carry in from the previous bit, one input bit from the first number, and one input bit from the second number. So with these 3 inputs, we will add these up together and we'll produce the result called sum. And then we'll also produce a C out. So these 2 are outputs over here. And now I know you haven't seen a truth table that has 2 outputs yet, but really it could be just 2 truth tables, one with C out and another one with sum put right here. But we're just conserving space by, since the inputs are the same, we're just conserving space by putting 2 outputs right next to each other, and they all use the same inputs. So if what we're adding is a 0 and a 0, and the carry in is also a 0, see that's this case. One number from the input is a 0, another one is a 0, and a 0 for the carry in. Well, the sum will be 0, and there will be no carry out. Okay. Now, what about, for instance, this case right here? The carry in is a 0, one letter is a 0, and one letter is a 1. So in that case, the answer is a 1, but our carry up here is a 0. Okay, and that's going to be the same for this case. Carry is going to be a 0. Now in this case, we're adding no carry and then 2 ones. That's this case right here, and our answer is 2, so our sum is going to be a 0. Notice the answer right here is a 0 because we have 2 ones and a 0 as our carry in. Okay, and then the carry out, though, is going to be a 1. And so we can finish answering the rest of these, and let's make sure we get these on the right line here. So there's that. And now let's keep going with our answers. Of course, the sum is 1 and the carry out is 0. This is another 2. This is another 2. And in this final case where we have all ones, that will be a sum of 1 and a carry out of 1. Okay, so here is our truth table that we need to deal with. So for your homework, ignore this column right here and do a sum of product or product of sum for the sum column. Come up with your equation up here, whatever one is the smallest, and since there's 4, you can choose either one. They're both going to be the same size, whether you do sum of products or product of sum. Okay. After you come up with the equation, you can say sum equals that equation that you got by looking at this column and ignoring that one. Next, do the C out. Okay. And in the C out, ignore this column and come up with the sum of products or product of sum for this column. And so then you'll have 2 Boolean algebra equations, and you build a circuit using the same switches, but they're going to split off and do the 2 different operations. So then you open up Logisim and you create your circuit. So you have your sum equals some equation, put down a input for C in, an input for C out, and an input for C in, an input for A, and an input for B. Create your circuit, and then the output here becomes a sum, and you can even label it. So you go, okay, that's my sum. Now, this is not the right circuit that you need. This is what the example I showed you. Then you can take the same input wires and drag them down to another circuit, and you're going to create, following the equation you got for C out, you're going to create another circuit, and then that output you can call C out. So again, you have 3 inputs, the C in, the A, and the B, that calculate the sum, and they also come down to another circuit that calculate your C out. So it's the same wires coming in, we just split them off and send them into 2 different circuits to get your 2 outputs. And then when you click up here, you have your, it's called the circuit name. You might as well go ahead, instead of calling it main, call it the full adder. Now, if you notice, your homework requires you to do this truth table that has the sum and the C out, and finally, one other truth table that's for a multiplexer, or MUX for short. So you can read about the MUX in this lecture, and this is the truth table for the MUX. So you have an A, B, and S input, and then just an O for output, and this is a third product of sums or sum of products that you'll need to create. And once again, it's 4, 4, so you can decide which one you want to do. I recommend just doing sum of products because that tends to be a little bit easier for all 3 different truth tables. Now this is like 2 truth tables in one, and then you have one more that you need to create, but it has different inputs. And in fact, we're going to put this down on a different circuit. So we have our full adder circuit here, and we want to create a circuit for MUX. So we can just click this little plus button right here, create a new circuit name. We could call it MUX, or you could multiplexer, and then put down your A, B, and S inputs. Go ahead, you create your sum of products or product to sum circuit, and then you have the O output right there. And in this case, we only have one output, so one circuit with the A, B, and S inputs. So once you have all of those, then you'll just need to create a video with your full adder and your mux. And in fact, your entire project is going to be contained within this same file. You're just going to add more and more circuits, but they're all going to get saved into one file. Besides doing for practice assignment, your lab project should be contained all within one file. You don't want to save different files for your different circuits. You want the circuits added together. Because the really cool thing is we can add another circuit in this one I'll call main. So now I have this main circuit here, but I could grab down my full adder. And if you notice, it's kind of like a little microchip that I packaged this circuit up here. I packaged this all up and I made it so that I can press more than one. And then on my main circuit over here, and I just double click to change circuits, I can grab a bunch of, like, say, 16 full adders and place it down. That way I don't have to copy and paste this circuit 16 times. I just grab my full adder chip and I place it down, and it has the A, B, or the carry in and the A and B inputs, and it has the sum and the Cout outputs in it. I can lay 16 of them down and create my circuit can add two 16 numbers together. So that's how this will be really easy for you. And once you have created the full adder circuit and the mux circuit, then go ahead and create your video, pass it off.